Do you feel the vibes?
Right, so if you remember in the last lesson, I said in math, there are 3 ways to solve something, right? And it's graphically, numerically, and analytically. We did graphically and numerically yesterday. Today we're going to do analytically, which is the same as algebraically, right? Just by doing like some algebra. All right, so you can put away your calculators for the time being. We don't need them right now. Okay, so let's talk about some properties of limits, right? What is the limit as x approaches c of k? Now, in limit notation, we know limit notation looks like this, right? So this number, the thing that goes here is the function. So in this case, this is the function. So this is y equals k. Now, we know what y equals k looks like, right? What kind of line is it? It's a horizontal line, right? So as x approaches, so if it's a horizontal line, what's the y value always? Whatever the thing is, right? So the limit as x approaches c of k is k. So for example, let's do the limit of 3 as x approaches 2. So this means this is y equals 3, which looks like this. Okay? So as x approaches 2, what's the y value approaching? 3, right? That's it. So it's just 3, right? No math involved there. Right. But what if you have the limit as x approaches c of x? Now c, y equals x, is the identity function, right? So y equals x. So as x approaches 1, what is y approaching? 1. And as x approaches 5, 5, right? But as x approaches 3, 3. Okay? All right. These are the building blocks. These are like the cells to everything, all living things limits, right? We can just combine these in different ways and get the limit properties for everything. So if you have a function f of x and the limit as x approaches c is L, and you have a function g of x and the limit as x approaches c is M, then you have the sum rule. The limit as x approaches c, f of x plus g of x is just the sum of the limits. Or if you're subtracting, it's the difference of the limits. If you multiply the functions, the limit as x approaches c is the product of the limits. K times f of x, it's just k times the limit. Dividing is the quotient, and so on. And then if I have f of x raised to a power, then it's the limit raised to a power. So for example, suppose limit as x approaches c. So suppose f of x is just x, right? And let's make that as x approaches 3. What's the limit of this? 3. But now, if I took x and I squared it, then I would also square the limit, and it would just be 9. Okay? All right. So here we go. Let's use the properties of limits to evaluate this. So the limit as x approaches 2 of 3, how much? 3. The limit as x approaches root 2 of e, because the function is y equals e, so it's at, e, 2.718, so it's e. Okay, now, so we talked about a constant, we talked about x, and we talked about that x raised to a power, right? So do you see how, but with these 3, you can build any polynomial function you want, because it's a number times like x to the power, right? So if you have a polynomial function, if you want to find the limit of a polynomial function, at x equals c, you just do direct substitution and it's p of c, right? You just use direct substitution. For rational functions, okay, it's the same thing again, p of c over q of c. But now we have a situation if the denominator equals 0. If the denominator equals 0 when you plugged in the value for the limit, then the limit cannot be found by direct substitution. It is not completely a hopeless situation. You just have to find a different way to evaluate the limit. Okay, so why don't we just go case by case here? All right, let's use direct substitution to find each limit. So here, I want to find the limit as x approaches 2. I can do this by direct substitution. So I can just say 2 minus 3 over 2 times 2 squared minus 2 minus 15. So how much is that? Negative 1 over negative 9? 1/9. Okay, let's talk about notation. You see how this is limit as x approaches 2? The minute you do direct substitution and you enter the number into the function, you have to get rid of the limit notation, okay? Because now the limit has this idea of approaching to something. Once you plug the value in there, it's no longer approaching anything. Now it equals that value. So you cannot put limit here. It will be points off, all right? Okay, so for b, we put negative 1 in here. So that's just root 2, and that's good enough. Here, negative 8 plus 6, what's that? Which doesn't work, so it's DNE. We're not getting imaginary numbers, this is DNE. But also, let's see why. Let's see what's happening here. The square root of x plus 6 looks like this, right? Where this is negative 6. And where is negative 8? Here. Right, you're not approaching anything. Like you're right, like you can't, the graph isn't approaching anything there. So it's DNE. All right? Okay. And then here, as x approaches a, we just plug a in here. And that's it. Cool? Cool. Okay. Now, let's talk about indeterminate form. Okay? When you do direct substitution and you have a rational function and you get 0 over 0, it is described to be indeterminate form because it's impossible to determine whether there is a limit or it does not exist. So when you get 0 over 0, don't just discount it and say, does not exist. No. It could very well be that the limit exists, or it could be that the limit does not exist. The point is, we don't know. We are not able to determine, so it is indeterminate, okay? So it is necessary to use other methods to determine the limit, and it could be that the limit exists, which is the same as converges, or it might diverge into negative or positive infinity. Do you see how the words keep coming back, right? Like the higher up you go in math, the more it's like math nirvana, where everything is like related to each other, right? Okay, all right. So let's take a look here. When you put negative 2 into this function, you definitely get 0 in the bottom, but you also get 0 in the numerator. So this is going to be 0 over 0. Okay, so we're not going to give up on this yet. What we're going to do is we're going to try to factor. Now, if we're going to work on this problem, like using algebra, the limit notation has to come with us at every single step. So this is the limit as x approaches negative 2. Oh, so the denominator is x plus 2, but I got to do a little bit of factor by grouping here. X squared, x minus 3, minus 4, x minus 3. This is the limit as x approaches negative 2. X minus 3 x squared minus 4, x plus 2. Oh my gosh, this is shaping out rather nicely, actually. Can you see what's going to happen? Yeah, it's going to cancel out. So this is the limit as x approaches negative 2, x plus 2, x minus 2, x minus 3, over x plus 2, cancels. So what I have now is x minus 2, x minus 3. Now, the thing that gave me 0 over 0, that issue is no longer present. So now I can plug in negative 2, but this time I have to drop the limit, right? So it'll be negative 2 minus 2, negative 2 minus 6. How much is that? Negative 4 times negative 8. Is it 32? I don't know. Oh, it's negative 3. So then it's 20. Right? So the limit is 20. All right? Any questions? All right, so one other thing is, right, you see how like this is like convention, like we just put like 0 over 0. This is like agreed upon, kind of like, we all know what that means, okay? All right, so this one too, when you put in 6, you get 0 over 0. So we're going to have to factor this. Let's go ahead and do that. This is the limit. X approaches 6. How does this factor? X minus 6, x minus 1 over, what is it, 7 and 6? Does that work? No. That's not 7 and 6. Oh, yeah, it is. Okay. Right? Yes, because we haven't done anything yet. But now the x minus 6's cancel. So the limit as x approaches 6, x minus 1 over 3x plus 7 is 5 over 18 plus 7. Is that 25? So 1/5. Is that right? Yep. Yes. Yes. Okay. You guys have to check my work on this because I usually have like my worked out solutions. I don't have it today, so I'm just like flying solo here. Like this is like all live. Okay. So, watch for mistakes. Okay. The next is rationalizing. I just didn't put them out. I haven't had time. So, okay, take a look at this one. You plug 25 into the numerator, you get 0. Root 25 is 5 minus 5, you get 0 again. In this situation, there is nothing to factor, so we have to figure out something else to do. Well, what you do when you have a square root situation like this is you rationalize. Now, I know we've always said rationalize the denominator, but know that in this situation, you can rationalize top or bottom. You just have to rationalize something. So here to rationalize, I have to multiply by the conjugate. Remember that word? Okay, now don't go ahead of me here, please. Because look, this is the limit as x approaches 25. And now, I know you all have this like urge to multiply. I like to FOIL that numerator there. Do not do that. Just copy it over. Because here when you multiply this, what happens? Square the first one, you get x. Square the second one, you get 25. Minus in the middle, and look at what happens. What happens? Cancels, right? So don't FOIL. If you FOIL, this doesn't happen as beautifully. So limit as x approaches 25, root x plus 5 is what we have. Now you plug it in, so it's root 25 plus 5, 10. Okay? Now, limit, no limit. And it is like minus 1 each time you don't have a limit. Okay? All right. So even in like Calc BC, right? Something as seemingly small as this on the AP test, you will lose credit, like you lose a point if you don't have your limit notation where you have to. No, I know what he's saying. No, you can just put this, but in your work, as you're simplifying, you have to limit, okay? Correct, and I have it here. But here and here you have to limit. No limit. Because you've plugged in the value, so it's no longer approaching anything. It now equals that number, right? Here you're looking for the limit. When you plug it in, this is no longer a limit. This is now f of c, right? So no more limit. Now you're actually like evaluating the function at that point, okay? All right, so here when you put in 0, 2 minus root 4, which is 2, so 0 over 0, not cool. But again, right, don't give up on them yet, right? So let's rationalize. What's the conjugate here? Right. Awesome. So multiply in, so this is limit as x approaches 0. Multiply, where you with the conjugate, right, where you wrote the conjugate. So this will be the square of this 4, the square of this x plus 4 minus in the middle. Lots of students miss that minus and then it's like points off, so just be careful, right? And then here you have x times 2 plus root x plus 4. Don't multiply it in. So here I have the limit as x approaches 0. So how much is this? This is 4 minus x minus 4. So what do I have left there? Negative x over x, 2 plus x plus 4 in the square root. X's cancel. So now what I have is the limit as x approaches 0, negative 1 over 2 plus root x plus 4. Now I plug it in. So I have negative 1 over 2 plus 2, 4. Okay. All right. One more thing. One of the objectives for Algebra 2 and Precalc Honors is to make you elegant and sophisticated math students. Part of that is when you have your steps written like this, to put equal signs in between your steps, right? You see all my equal signs over there? You have to have those, right? Because if you don't have these equal signs, right? If you don't have these equal signs, then it's just stuff. It's just gibberish. And we don't do that, right? It's like, would you ever write an essay and not put any punctuation? Okay, I take that back because I've seen how you guys write emails. But also though, would you write an essay and just not put any punctuation? It's just gibberish after a while, right? So it's the same sort of thing, okay? All right. Again, like sophisticated math student, right? Like just don't be, like this is like self-respect, right? Like you would never like let anybody catch you without like equal signs everywhere, right? It's embarrassing, right? It's embarrassing. Okay, so here we go. What about at infinity? Okay, so if you have x to the n, right? The limit as x approaches infinity, right, will be infinity, right? Let's think about that. If x is infinitely large, like a trillion to an exponent is even larger. So it's infinitely large. But now let's talk about negative infinity, right? If you have the limit as x approaches negative infinity, then if n is even, right, it'll approach infinity. If n is odd, it'll approach negative infinity, right? So look at this. For even functions like this one, as you approach the limit as x approaches infinity will be infinity, negative infinity will be infinity because this is even. But if it's odd, right, as x approaches positive infinity, you go to positive infinity, and then here you go to negative infinity. Okay. Now, polynomial functions. Remember when we talked about end behavior for polynomial functions? We only look at the leading term. Okay, just recalling that. Okay, so let's talk about this. Evaluate each limit. This is a polynomial function. The only thing I'm going to look at is the leading term. So as x approaches infinity, is this going to go to infinity or negative infinity? Infinity. That's it. That's all. No work here. No work. Oh, yeah. Thank you. I was so focused on the no work. Thank you, Oren. You get an A. Okay. Huh? Wait, what did he say? All right. Negative. Okay, so this one. What do you think? Negative or positive? Oh. Yep. No, you don't have to put the positive. I started writing negative and then I made it a positive. Okay, what about this one? Oh, yeah, that one. Negative infinity. What about this one? Awesome. Easy, right? And fun, right? Yeah, there you go. Yeah. Okay. Those were polynomial functions. It's all nice and easy. Well, okay, so what about reciprocal functions? Well, this one too is super easy because if you have 1 over x, as x approaches infinity, now you have 1 over a large number which will approach to 0. Okay, so let's think about that again. If you have 1 pizza and you have to divide it among 1,000,000,000 people, how much pizza does each person get? Practically 0. Okay? Okay, so now, so then for any positive integer, 1 over x to the n, right? If you have 1 over x to the n, as the limit approaches positive or negative infinity, the whole thing will approach 0. Okay. Now, one thing. When we were looking at functions, the limit approaching like a 5, 3, negative 2, we were doing direct substitution, remember? And we were plugging in the numbers. In the case of infinity, so for instance, if you have the limit as x approaches infinity of like 3x, you are never allowed to write this. Never allow. Oh, you laugh, but you have no idea what I've seen, right? Or you're never allowed to write this. This is absolutely not okay. This is not okay because infinity is not a defined value, so we cannot have mathematical expressions with it, all right? But you can reason things out. Okay, so here we go. This is again a review. Rational functions at infinity. You have to compare the degree of the numerator and the denominator, just like we were doing with like that number 41 or whatever, right? So if the degree of the numerator is less than the denominator, then the limit is 0. So here we want the limit as x approaches infinity. Compare this. So let's just see what exactly is happening here. Limit, this is equal to the limit as x approaches infinity, x squared over x cubed, which is the limit as x approaches infinity, 1 over x. And I know that when x gets infinitely large, 1 over x will be equal to 0. Okay? Now, all you have to do is just put 0. You don't have to show any work for this one, okay? No work for this one, okay? Right. Okay, this is the one where you don't have to show any work. Okay. Correct. And then if the numerator and the denominator have equal degree, then it's just the ratio of the leading coefficient. So in this case, right, this will just be -2/6, -1/3. No limit. No limit because it's just the value. Like the limit is -1/3. Okay? Here, if the numerator has a higher degree than the denominator, then this over this, what do you think? So now this is going to reduce to -x², right? So, and then as x approaches infinity, is it going to go to infinity or negative infinity? Negative infinity. Right? Fabulous. Okay, so what about this one? What do you think? Highest power over leading term over leading term? 0. Leading term over leading term. Who says 0? Who says negative infinity? Who says positive infinity? Is it negative infinity? What does this reduce to? Negative x. And then when x approaches infinity, it will be negative infinity. Yeah. Because, right, when the numerator is bigger, then it'll be to infinity. Only when they're equal do you look at the coefficients. Okay, what about this one? 7/2. Okay, so let's do some piecewise functions. Yay is right. To evaluate limits of piecewise functions, you want to look at the left-hand limit and the right-hand limit. Okay? If the two limits are equal to each other, then the limit exists. Okay? So, this is what we're going to do here. This is where you have to show justification. So this is what we do. Limit 3 from the minus side. Where do we plug in the 3? Right. Oh, you know what? I thought I fixed this. So these should all be labeled f of x. Okay? So limit as x approaches negative 3 from the minus side of f of x is equal to, 3 times 3 plus 7. How much is that? 13. And then the limit of f of x as x approaches 3 from the plus side, that will be 9 minus 1, 8, right? Right. So limit of f of x as x approaches 3 from the minus side is not equal to the limit as x approaches 3 from the positive side. Therefore, limit does not exist. Okay? Yeah. Okay, so here we go. This one, the limit as x approaches -1 from the minus side of f of x. How much is that? -1? No. 3. 3. And then the limit as x approaches -1 from the positive side of f of x. 3. So the limit of f of x as x approaches 1 is equal to 3. Okay? All right. Yeah, we did this in chapter 1. It doesn't matter. That one doesn't matter. It's supposed to be lowercase. Doesn't matter. I recalled that, and then I realized later, I was like, no, wait, I was thinking something, right? So it doesn't matter. Yeah. No. Okay, and we are going to stop here for today and then do these word problems tomorrow. Okay? Yep. No.
Press start.